I hope we aren't too surprised by the fact that advanced functions starts by talking about functions. More specifically, we're talking about a subset of functions known as power functions. These are a subset of polynomials. Polynomial functions have the form that function of x is equal to a polynomial that includes x in one or more terms. So n is a whole number, the exponent here. Now, the coefficients here are real numbers, so there's no square root of -1 shenanigans. So no imaginary numbers. X is a variable, and n, the greatest power of x, is a degree of the function. So say we have, y equals x to the 4th power. That's degree 4. Now, a subscript n, is the leading coefficient. So it's a coefficient of the highest degree term. In case you get asked what the leading coefficient of a particular polynomial is. Usually this term doesn't see that much use, but it's good to know nonetheless. A subscript 0 here is a constant term. It is multiplied by x to the 0th power. You can think of it that way, but there's a problem here. 0 to the 0th power is undefined, so at that point you can't think of it as, x to the n all the way to x to the 1st power and then x to the 0th anymore. Otherwise you would get no value, undefined. Now, a power function is a function in this form. As we can see, this is a monomial. There's only one term here. We have a whole number exponent of x, and a is the only coefficient. Power functions have a number of common characteristics. For example, if we have an even degree power function, what happens? Well, we know that it's going to end up going positive on both sides. And at what rate will it go positive? Well, say -2 to the whatever power and +2 to the whatever power. As long as it ends up being an even power, the negative signs all just cancel out. So it's just 2 to the whatever power versus 2 to the whatever power. So it's symmetric about the y-axis, or specifically the line x equals 0. Because sometimes you see the y-axis drawn in places where it's not x equals 0. For example, let's say we have a graph where we are only looking at the values from x equals 1900 to x equals 2000, and we're trying to model something. Where are we going to put the y-axis? No, we're not going to put it way off the chart. Of course we're going to put it on the left side. Odd degree functions have point symmetry about 0, 0. What does this mean? This means that, say you have a point over here, you go directly across to a point over here. Say you have a point over here, well, you go across from there to somewhere around here. So point symmetry, unlike a line where you draw a line and do another line of the same length on the other side, and this line is perpendicular to the axis, or whatever line of symmetry you're dealing with. Unlike line symmetry, point symmetry goes through that point on the same direction and the same distance to either side. Please note that same distance to either side specifies the point to either side. It doesn't end up being the same direction. Why? Well, in vectors, we'll talk about how, walk 5 meters east versus walk 5 meters west. It's the same distance, but they're completely different things. I'm pretty sure we're all familiar with the concept that walking east and walking west are different things, yes? So to go into positive direction versus negative negative, well, that's different. Whereas the distance we can mention as being the same. So example 1, functions and graphs. Y equals x is the simplest that we can have. And when we graph it, it looks like this. I do not think this is very complicated. But when we get to y equals x to the third power, let's compare that with y equals x. So this here is y equals x, and this here is y equals x to the third power. And y equals x to the fifth power, we also compare to y equals x. What's the difference between these? Well, with the third power, we stay low for a while. Then once we get to 1, we reach 1. So x equals 1, y equals 1. And down here it's negative 1, negative 1. Okay, what really matters? What happens when we go to positive infinity? And what happens when we go to negative infinity? Oh, hey, this goes to and this end goes to negative infinity. What about this? Same thing. It goes to positive infinity as x approaches positive infinity. And this goes to negative infinity. So the quadrant system has this being the first quadrant, this being the second quadrant, this the third quadrant, and this the fourth quadrant. So with the odd functions, we will end up with quadrants that are across from each other. Why? What if we take, say, negative x to the fifth or something? Well, we would end up, instead of going one way in the end, we go the exact opposite. So, flipped. Now, how about these? So, even functions. Well, clearly we can see that the end behavior is very different for y equals x squared compared to y equals x. And we see that there is a minimum right here. So for even power, we have vertex. Well, okay, we should probably specify that it has to be a function. There's a vertex, so a maximum or a minimum. And both end behaviors match. Although this shouldn't be a surprise given it's supposed to be symmetrical about x equals 0. Here we see that as we get bigger and bigger even exponents, what happens is that it'll still go through 1, 1 and 0, 0 and negative 1, 1. Sure, it'll still go through these points, but it will end up shooting up much more steeply after that if you get a bigger exponent. Now, I don't think this is too much of a surprise for anybody who has ever taken an exponent of anything and actually solved for it. Why? Oh, hey, 2 to the 4th power is going to be smaller than 2 to the 6th power, which is going to be smaller than 2 to the 8th, smaller than 2 to the 10th, and so on. Yeah, that's not too much of a surprise. Hence why it shoots up much faster if you use a bigger even exponent. And on this side, it does the same because it's symmetrical. And because, well, the negative signs get cancelled out by the even exponent. Here we contrast x to the 10th power with, well, let's see. This is also a parabola, or rather, this is a parabola because technically parabolas are only quadratic. Let's say we didn't know it was a parabola. How could we figure this out? Oh, hey, this goes through 2, 4. What power of 2 gives us 4? Yeah, I don't think this is much of a surprise. So this here is y equals x to the 10th. It is a good habit to always label all the lines that you draw on your diagrams. So we notice that this also still passes through 1, 1, and negative 1, 1, and of course 0, 0. So we contrast a larger even exponent with a smaller one. We notice that the larger exponent has lower values when it is between 0 and, well, plus minus 1. Because we know that taking the exponent of a number less than 1, or between plus and minus 1 rather, will end up making that number smaller. Because, 0.9 squared is 0.81, and the principle just keeps on being applied. Okay, here's another example. So identify polynomial functions, state the degree and leading coefficient of each polynomial function, if it is one. So here we have a polynomial, because they're all x to the some power, including 0, and all have coefficients. So the degree for leading coefficient five. Because, oh hey, 5. Well, here we have negative 7 times x to the 5th. So the degree is 5. And the leading coefficient is negative 7. Negative 7. Here we have y equals sine x plus cosine x squared. This is not a polynomial function. This is actually two different sinusoidal functions added together. So, not a polynomial function. Here, this is y equals 5x to the 4th power. This gives us a highest degree term with degree. And 4 and leading coefficient. Okay, so hopefully we still remember interval notation, because this is what we will use to talk about domain and range. In brackets, these round circles mean strictly less than or strictly greater than. So if we were to draw this on a number line, and this was A, this was B, we would have of course you might have to use a little bit more scribbling just to make sure the line's obvious. Well, we would have this. Now, what happens if we have one end as a square bracket? Well, a square bracket is less than or equal to or greater than or equal to. So, a circle and a filled-in circle. A filled-in circle indicates that that end, that particular point, is included, whereas a blank circle says that, oh, this particular point is not included, but every value up to it is included. So this is A and this is B. And of course, if we have the square bracket on the other side, we would have the filled circle, most predictably, on the other side. Sometimes you see this drawn differently instead, such as what I'll do for this next one, which is this case. Sometimes you see it drawn like this. So this sort of thing is more often used when you have to compare and contrast, say, multiple intervals. Like this. What's the overlap between these two intervals? Well, it's going to end up being this piece here. Although we're not doing that for now. So union of sets and so on. Now, here, what happens if we go off to infinity in either direction? Well, we do whatever the symbol is supposed to be. So empty bracket or filled-in bracket. And we use a thicker than normal line to one end, including the arrow. And then the other end of the line is perfectly normal. Okay. What happens if it's just the entire number line? Oh yeah, in this particular case, I should probably label this as B, corresponding to, well, this diagram. What happens if it's the entire number line? Well, you just bold the entire line, and that's it. Or alternatively, you can do something much simpler and just write x is an element of the real numbers. And then write nothing else. That's from negative infinity to positive infinity, not inclusive, because infinity is not a real number. It has no particular value. So, in review, domain is the set of the independent variable of a relation. Range is a set of the dependent variable of a relation. Note that we said relation instead of function. But these concepts apply exactly the same way to functions, because functions are a type of relation. The end behavior of a graph is the y value as x approaches positive infinity and as it approaches negative infinity. Now the end behavior may be the same or it may diverge. So here we're going to determine the domain and range and end behavior of each power function. Negative 0.5 x to the fourth power. Is there any x value for which this has no value? Well, no. I mean, other than plus infinity, but because what you'd get is negative infinity, which is not a real number, but that doesn't count. We just say domain is x is an element of the real numbers. Or, well, with set notation, we write this. Some places let you get away without the set brackets. So the domain is x is an element of the real numbers. The range would be, well, negative 0.5 times, so it's opening downward, and Well, is this moved up from having the biggest possible value this can reach be at x equals 0? So 0? Well, no. So range is an element of the real numbers. And what else? Well, we know that y is less than or equal to 0. Some places you will be asked to write, oh, y is less than or equal to 0 and is greater than negative infinity. Other teachers will not ask you for this part. Or alternatively, what we could have written for range was, oh, y is an element of the set of negative infinity to 0, inclusive at 0, not inclusive of negative infinity. So, what is the end behavior? Y approaches negative infinity for both ends. And here's the graph. Graphing calculators are very popular these days for doing problems, but we do point out that many contests and some exams even don't allow them, which of course is a problem if you're dependent on graphing calculators. So here we have another problem. Here we have x to the 5th power. Is there any point where we have no y value? So the domain is well, if we're going to write interval notation instead of set notation, we would write x is from negative infinity to positive infinity. So range is the same. I mean, it's 1/8 times x to the 5th. But when you get toward negative infinity for x, you get to negative infinity for y. Or toward, because you can never get to that. So it's for positive, same thing happens. So, what about end behavior? End behavior can be marked by points. Thus indicating that at x equals negative infinity, we get to y equals negative infinity, and positive infinity, positive infinity. So here we have the graph. And hopefully this review of power functions has been useful in terms of remembering the concept of point symmetry versus line symmetry. So point symmetry is for odd functions, line symmetry is for even functions. I know it's usually called odd powered and even powered, but after a while most people tend to just not bother saying the power part. So we hopefully remember the 4 quadrants, and we can conclude the end behaviors depending on the particular powers we're given, and of course the coefficients. So that's it for this section, and we'll see each other again then next section.